We have covered in the previous video the normal and tangential components for the kinetics. Let us look now at a quick example which makes use of that coordinate system. So a girl having a mass of 15 kilograms sits motionless relative to the surface of a horizontal platform at a distance of r is equal to 5 meters from the center. And you can see a nice schematic which is shown here on the right. If the angular motion of the platform is slowly increased so that the girl's tangential component of acceleration can be neglected, so we can assume dv over dt is close to 0, determine the maximum speed which the girl will have before she begins to slip off the platform. The coefficient of static friction is equal to mu s equals to 0.2. So one thing to note about the given is that we're asked to find the maximum speed before the girl slips off the platform. And if you remember from the lecture on friction, we've said whenever a body is on the verge of slipping, we need to make use of the static friction and not the kinetic friction. And that's exactly why they gave us mu s and not mu k. So I'll give you a couple of minutes to try to solve this problem, which deals with the normal and tangential coordinate system. And you can simply watch the solution later on. So step 1 involves writing down what we know. There's a lot to write about the given. First, we have the mass of the girl, which is 15 kilograms. We have the velocity of the girl with respect to the platform, which is the relative velocity, which is equal to 0 in that case. We're given the radius or the distance from the center of the platform to the girl, which is equal to 5 meters. We know that the tangential component of acceleration can be assumed 0, and we're given mu s is equal to 0.2. We're asked to find the maximum velocity before slipping. So just before it slips, what can we conclude? First, we're dealing with static friction, and so the frictional force is equal to mu s n. Since we're given a radius which is equal to 5 and a platform which rotates, we know that we're dealing with a curvilinear motion or a curvilinear path with rho is equal to r is equal to 5 meters. Looking at the girl and noticing that the weight is directed downwards, so not along the plane of motion, we know that we're dealing with a three-dimensional space for the problem. And then finally, one thing to always keep in mind when you're asked to calculate the velocity at a specific instant is the link between the velocity at a specific instant and the normal component of acceleration an. So we know that an at a specific instant is equal to v squared over r, or rho, which is the radius of curvature. So the next step is obviously to draw the free body diagram. We have opted for a normal and tangential coordinate system since we are given information about that system. So let us draw the positive sign convention. So we have T, N, and B as shown here. We can now draw the different forces acting on the body. I have represented the girl here as a circle. It is subject to its own weight along the B axis, which is 15 times 9.81. It has a normal reaction force due to the platform, which is N, and a frictional force which is acting inwards, and it's equal to 0.2 times N. Now you might be wondering why the frictional force actually acts radially and not tangentially, and I'll explain that. So you should always remember, whenever you have an object sitting on a rotating platform, there is a virtual force that pushes the object outwards. And so if you remember from the friction lecture, we know that friction always opposes motion. And so if you want to think about this virtual force, which does not appear here on the diagram since it's virtual, pushing you outwards, the frictional force needs to push you inwards. So it needs to resist motion, and so that's why it's radially inward. And that's very important to keep in mind when solving problems. So now that we have labeled all the different forces acting on the body, we can draw the kinetic diagram in step 3. Since we know that at is equal to 0, we only have a single component of acceleration, and that's the normal acceleration. So we can sketch that NAN, always directed inward towards the center of rotation. And so now that we have the two diagrams, we have fully understood the different forces acting, the different accelerations we expect, we can write down the equations of motion. So we have three different equations of motion: sigma fb, sigma fn, and sigma ft. Now noting that there are no forces along the t-axis, it means that there are no acceleration as well, and so the equation of motion along the t-axis is useless here. So let us write down the two other equations. Sigma fb is equal to 0. Obviously we do not expect the girl to jump off the platform vertically, so A is equal to 0 there. We can write down the equation: the sum of the forces is equal to n minus 15 times 9.81 equals to 0. Then we get the normal force. N is equal to 147.15. Now writing the equation for the normal component: sigma fn is equal to man, 0.2 times n is equal to man. We know the value of the normal force, which we have found from the previous equation. We can replace that in this equation and get the value for an, which is 0.5096 meter per second square. So now that we have an, remember from what we said in step 1, an is related to the velocity at the instant itself. So we can find the velocity from there. So an is equal to Vmax squared divided by r, which gives us Vmax is equal to 3.13 meter per second. So that's a relatively easy problem which involves the normal and tangential components. Just one thing to keep in mind is whenever you have an object which rotates around a platform, the frictional force is always directed inwards, since it tries to resist this frictional force that's being developed by the rotation.